So the other thing that you guys are going to be working on is writing and balancing chemical equations. Basically, it's writing a sentence in chemistry speak is what chemical equations are. One of the most important things for chemical equations is that they are balanced, okay? Meaning that you have the same amount of things on each side of the equation. And what it represents is the number of elements slash compounds that are undergoing a reaction. And we're going to use chemical symbols, from the periodic table, and correct compounds, neutral formulas for ionic compounds, to show what's reacting. And the whole reason why we have to balance the chemical reactions is because of the law of conservation of matter, right? So if you say that you have one water molecule going in, yet you have like 5 oxygen atoms coming out, or oxygen molecules coming out, so like you have some reaction and you have 1 water molecule, and you're saying that you have not even 5, if you just have a single oxygen molecule coming out with some other stuff, something with hydrogen in it. This doesn't make sense because you started with 1 oxygen, yet you're saying that you magically have 2. So the idea of balancing, we know that we're going to have to at least have 2 water molecules in order for this to work, and then we'll see how the balancing works from there. So we need to balance our chemical equations in order to satisfy the law of conservation of matter, and also the conservation of mass, which is related to that of matter. So it's just super important, and you can straight up tell me if the reaction is balanced or not. It's not something that I can, it's either balanced or it's not, and you can be the judge of, do you have the same amount of things on both sides? So when we're looking at chemical equations, we can write them in English words, right, where we say 1 methane molecule reacts with 2 oxygen molecules to form 1 carbon dioxide molecule and 2 water vapor molecules. So for us as chemists, we need to decode the substances that are being reacted and translate them into their formulas, right? So methane was one of our, I can't remember if I put it on our list of what we should know, but we've seen it a few times. Methane is CH4, so that's the common name, methane. You could also call it carbon tetrahydride. But that gets us that. Oxygen molecules, remember, oxygen is diatomic. So we would have to write O2, super important, because it changes the balancing if you don't have have a 2 as a subscript there. It changes the coefficient that goes in front. And it forms 1 carbon dioxide molecule, and we know that that is a molecular compound because of the naming, because it has the prefix, and 2 water vapor molecules. So we'll notice when we look, like, this is the English version of this chemistry sentence, right? This is saying the same exact thing, just in chemistry speak, in terms of the formulas and numbers and stuff like that. And a lot of some of the other things that we should notice in words. When something says that you're reacting, it means they're on the same side of the equation. We notice that on this side of the equation is what we're going to call the reactants. And on this side of the equation, on the right of the arrow, we're going to call that the products. Right? The reactants are on the left, products are on the right. Just like reading a sentence, we start on the left and move to the right. The reaction arrow tells us the difference between the products and reactants. So the font that I use has this really funky arrow, with like tail and stuff. But technically, our reaction arrow is just one single-headed forward-facing arrow, which is different than, remember, we had a resonance arrow that looked like this. That is not a reaction arrow. So the arrows have meaning here in chemistry. And then also in our words, how do we know when we're going from product to reactant? We use some type of word that says, and we formed, and we made, or we produced, something that is letting you know that these are changing into the new substances. And it just so happened in this example I gave you the numbers of how many we have are given to us. A lot of the time, we're going to have to figure out those numbers ourselves by balancing the equation, but take the numbers as you can. The other thing you'll see is we have states of matter. All of these happen to be gaseous, and some of the other states that we have, right, we have solid, we have liquid, we see gas, and then the other common one that you're going to see is aqueous, and we saw that with acids. But these are those are the states of matter that we're going to use. And knowing the state of matter, we're going to get to that quite a bit more as we are moving on. We're going to be able to predict our products in the state of matter. But for right now, in general, you're going to have to use keywords that are gonna, or your experience in life, to know the state of matter. So like oxygen, you breathe it in, it is necessary for life. You should understand that it is a gas molecule. Carbon dioxide, you also breathe that out. It's understood that it's a gas molecule. Now water, we know that we can deal with water in any of the three states. So the fact that they gave us the word vapor is the cue that that's a gas. And then methane, again, is one of those, if I told you it was natural gas, then you would be like, oh, it's gas. So it's through experience as we're looking at it. So pay attention to that. Like a true equation is completely balanced with states of matter. And I think Mastering Chemistry has been asking you to do states of matter anyway, so you might be used to it. So if we're looking at this, we notice that I'll get rid of this stuff, and then we can start looking at the amounts of things that we have. So here I have 1 carbon, and if we look on the other side, there is 1 carbon. So the carbons are balanced. Over here on this side, we have 4 hydrogens. And over here, it looks like we only have 2 in the water, but we have 2 water molecules, right? So we have this, we have oxygen with hydrogens, oxygens with hydrogens. So we do have a total of 4 hydrogens, and the coefficient, that's what we're going to call this number boxed in blue, is the coefficient. That belongs to everything in that compound. So we not only have 4 hydrogen atoms, but we also have 2 oxygen atoms. So the coefficient goes to everything in the compound behind it. Our subscript here, right? Our subscript only belongs to the thing that's right in front of it, the substance that's right in front of it. So this refers to just 2 hydrogens. Oopsies. Okay, so we do have a total of 4 hydrogens, and we can keep going as we're seeing this. I have 2 oxygens in my oxygen molecule, but I also have 2 oxygen molecules, so that's a total of 4 oxygens. Now, what happened on the other side is the oxygens get split and go into 2 different compounds. It goes into carbon dioxide, so we have 2 oxygens from there. And the other 2 oxygens go into 2 different water molecules, right? So each water molecule is 1 oxygen, but remember I have 2 water molecules, so there's a total of 2 in the water, 2 in the oxygen, 2 in the carbon dioxide, so we have a total of 4 oxygen like we have on the other side. So this equation is balanced. And these coefficients, if there's no coefficient, it's assumed to be 1. Okay, these coefficients are telling us the ratio of this substance, right? And you can think of this like a recipe. We're actually going to come back to that later on in the year. But in order to make 1 carbon dioxide and 2 waters, I need to mix together 1 methane and 2 oxygens. If I want to make 4 water molecules, then I need to double this recipe. We could treat it just like cooking. So if I had 1 dozen methane molecules, right, we come over here and I put a dozen in front of here, right, I would have to multiply the entire recipe, right? What could I make with a dozen methane molecules? Well, I could make a dozen carbon dioxide molecules and 2 dozen water molecules, as long as we have 2 dozen oxygen molecules, right? It is necessary and needed to have that oxygen. if I have 12 methane molecules, but I do not have the correct number of oxygen, then I can't make this reaction go. It's like trying to make pancakes with no eggs, right? You can't, you're limited by a certain amount. And we'll talk about like reaction stoichiometry when we get back from break. But basically, all I'm saying is these coefficients are ratios, just like we had in the previous video. Ooh, go up here. Where did it go? Oh yeah, here. So we see that our formula gives us mole ratios, right? And it tells us for every one water molecule, there are 2 hydrogen atoms and 1 oxygen atom, but you can also talk about moles. In 1 mole of water, there's 2 moles of hydrogen and 1 mole of oxygen. We're going to see the same exact thing happening here in our balanced equations. We're getting ratios. So if I have enough oxygen to react 12 moles of methane, then I can make 12 moles of carbon dioxide and 24 moles of water. So it's just a ratio. As long as your ratio stays the same, 12 to 24, right, is a 1 to 2 ratio, just like we have in this coefficient. When you're balancing these equations, you just need to make sure that you have the most simplified version of your coefficient. So if you did 2, 4, 2, 4, that's the same thing as a 1 to 2 to 1 to 2 ratio. So just simplify your ratios as much as you can. So like I said, when we're dealing with chemical equations, we balance them using coefficients. Okay, so the things that go in front, if you are writing equations and you have no coefficients in like 5 consecutive equations, something is wrong. So when you're writing your chemical equations, you need to have, right, most important, the correct formulas. That is the most important. So if you have a molecular compound, you are putting in the correct number that they're telling you. So if you have something that's like carbon tetrachloride, you need to make sure that your substance is CCl4, right? And if you're talking about an ionic compound, and even acid compounds, ionic and acids, you need to have neutral formulas. This is going to be the place where most people mess up, not having neutral things, because you're more worried about balancing first. You need, like, the most important thing is to have neutral formulas for ionic compounds and acids. And most important, have the correct formulas. But it's the ionics and acids that are going to get you. So with our chemical equations, we're going to balance using coefficients. We're going to include the states of matter. We have the special symbols and the places in which they go, showing that they're adding together. So you just do a plus sign. You have the reaction arrow. It's when we're looking here. Yeah, I'm going to write it now just so that we have it. Okay. When we are writing equations, you know what, this needs to be a little bit bigger. Okay, I cannot stress this enough that you need to make sure that you are getting neutral compounds first. So neutral compounds, more specifically correct formulas, but I'm just going to remind us that if it's ionic, you need to have a neutral compound. And if you do not have a neutral compound, then balancing your equation is going to be wrong, because if your formulas are wrong, your balancing is wrong. So when you're writing equations, we're going to write the symbols of the formulas and symbols of everything first, and then we are going to backtrack and start balancing. Okay, so here, we'll do these examples and then I'll throw in another example so that we can see this idea of neutral compounds first. So what I'd be asking you to do is write a balanced equation. Sometimes you're given the equation, you just have to balance it. Other times you're given the words and you have to write the equation and then also balance it. So liquid water decomposes into oxygen and hydrogen gas. So the other things you have to be aware of is diatomic elements. Because again, that's going to affect your balance. Okay, so liquid water. So we know the formula of water. The correct formula is H2O. They're telling us it's liquid. It decomposes. So here's a word that is telling us the water is turning into new things. So that's a key word to let us know that we are moving from the reactants to the products, and we are creating oxygen and hydrogen gas. Those are the natural states of hydrogen and oxygen, is diatomics and gas. So that's the first step, right? I need to make sure it's that you write the formulas correctly. So you might be tempted, if you were not thinking about neutral compounds first, or correct, I'm going to also do correct formulas / neutral compounds. They kind of mean the same thing. If you weren't paying attention to that, you might say this and go, oh yeah, right? H2 and 1O, now this is balanced. But that's not what happens, right? Oxygen, when it turns into an element, it goes into its elemental form, and its elemental form is O2. And now we have a way of balancing our reaction and saying, in order for this to happen, right, I have 2 oxygens on the right side, and I only have 1 oxygen on the left side if we're looking at oxygens. So we need to balance this out, meaning I need to get 2 oxygens on the left, and the way that we show that is by putting a 2 as a coefficient. Once you have the correct formulas and the neutral compounds, the only thing you can now do is write coefficients. Okay, that is, and a lot of the time I actually like to write or show this line here to say this is now where I can add things in order to balance the reaction. So I put a 2 on the left side to make sure I have the correct number of oxygens on both sides, but by doing that I have now changed the amount of hydrogens, which is fine, right? I have a total of 4 hydrogens on the left side. I just put a 2 as a coefficient in front of the hydrogen. So what this means to us is when water decomposes, we get twice the amount of moles of hydrogen than we do oxygen. And that's true. There are ways that you can show that. We don't have the apparatus that allows us to do it, but it is true. We do get twice as much hydrogen as we do oxygen. Okay. In this example, there are no neutral compounds to worry about because we don't have any ionic compounds, but if we did, we'd have to worry about that. So now nitrogen and oxygen gas react to form gaseous dinitrogen pentoxide. So here, again, we have to be aware of our diatomic elements. They're going to show up quite a bit. And if you look at all the examples we have, they all have a diatomic element in them. So we have nitrogen plus oxygen gas react to form gaseous dinitrogen pentoxide. So here's another important thing that we have to do. You might say, oh yeah, nitrogen and oxygen, N2O2 gives us N2O2, right? So like, oh, I don't have to balance anything, it's fine. But the formula that we are making is this, dinitrogen pentoxide. So we have N2O5, right? So correct formulas first, that's what we have, and then we come back in and we show coefficients. Then we can start balancing, and you're looking at this and you're like, the nitrogens are good, but the oxygens are not. When you're doing coefficients, we generally do whole number coefficients. So if you're looking at oxygen on the right side, we have 5, and if you're looking at oxygen on the left side, we only have 2. There's no common factor between 5 and 2, but what we could do is put a 2 in front of the N2O5. This now gives me 10 oxygens, so I would have to put a 5 in front of the O2. And yeah, I unbalanced my nitrogens, but how easy is it to just put a 2 in front of the nitrogen, right? So just because nitrogen was set at 2 doesn't mean it has to stay that way. It just happened to be working at the moment, but in order to balance our oxygens, we had to change that, and that is okay. It is okay to erase and change things, and once you say one thing is balanced, it might not stay balanced. So here's another example where we have a compound or a reaction that's already written for us. We just need to balance it. And if you don't see coefficients, do not assume that it's balanced. You can ask yourself, check. There's 2 carbons on the left. There's only 1 carbon on the right. I don't even have to go any further. I can tell myself this isn't balanced. So you need to balance it. You can't leave any equation unbalanced. So we would come back here and we would put a 2 in front of the carbon. Now the carbons are balanced. And it's a back and forth game. And it's okay to be going back and forth. There is some strategy to what you should do. Like looking at the oxygen next would probably not be a good idea, because if I try to balance out this oxygen, then and I get that set, then I have to worry about the hydrogen, and the oxygen is on both sides on the right side of the equation, so it gets a little messy. So because I have an empty oxygen, or I have oxygen by itself here on the left side, I want to leave that one to last, because whatever I do to the oxygen on the right side, I have an easy way of fixing it on the left side. So let's look at the hydrogen next. I have 6 on the right side, and I have 2 on the left side. Hydrogen only appears in water. So I would come in and I would put a 3 in front of this, and now I get it balanced. And now I can worry about the oxygen. Oxygen is in 2 places. I have 4 oxygens. Looks like 40. I'll just leave it at understanding that you guys know I'm looking at oxygen. I have 4 oxygen there, and I have a total of 3 oxygen here, giving me 7. And we find ourselves again, 2 and 7 don't have a common factor. So we're in a spot that's a little sticky and not as easy to change as what we had up above. So there's a little trick that we do, okay? And it's just a little math trick. If I have 7 oxygens on the right side and I put 7 over 2 on the left side, it is true that if I do 7/2 times 2, that gives me 7 oxygens, but we don't like to have fractions. So the trick is put the fraction to say, okay, in order to get 7 oxygens, this is what I would have to do, but then I want to get rid of the fraction. So I'd have to multiply everything by 2. So instead of leaving that as 7/2, I'm going to change this. I'm going to say 2, 7, 4. I'm going to multiply everything by 2, and 6. Okay, so just a quick, did that actually work? We have 8 oxygens over here, 6 on this side, 14. 7 times 2 is 14. So I've balanced my oxygens. In carbon, I have 2 times 2 is 4, 4, 2 times 6 is 12 for the hydrogen, 2 times 6 is 12. So that worked out, and that's a little trick that we use. We could have done the same thing over here. I'm actually just going to go back and show. So the oxygens are good, or the nitrogens are good, the oxygen is not. So if I did 5/2, right, that gets me a trick, the fraction trick, to getting to 5 oxygens, but we don't want to leave it as a fraction, so we multiply everything by 2, and we get back to the balance that we had. So it's the same math trick that we're doing. You guys can work on that one over here. N2 plus H2 is NH3, but I just wanted to show, if we said sodium reacts with chlorine to form sodium chloride. Okay, if we wanted to write this reaction, I'm trying to get us an example of correct formulas, neutral compounds first. Okay, so sodium is a metal. If you go look on the periodic table in the classroom, it's black, meaning that it's a solid at room temperature. So sodium is reacting with chlorine, which is a gas. Again, the periodic table is going to tell us that. And it is going to form sodium chloride. This, if you don't focus on neutral products first, this is where everybody's going to go, oh yeah, we formed sodium chloride. Awesome. And I'm going to say powder to tell you that it's a solid. And you'd be like, yeah, this is great. But then you did not make sure that you have a neutral compound between sodium and chlorine. So I identify this as an ionic compound. And I have to tell myself, okay, sodium's +1, chlorine's -1. When you crisscross, this needs to be sodium chloride. right? So neutral products first, and then we can come in and start balancing. The chlorines are unbalanced, so I put a 2 in front of the sodium chloride, and then a 2 in front of the sodium. Okay, so this is our balanced equation. Again, if you find yourself not putting any coefficients into multiple equations when you're writing them, then something's wrong. You need to go back and check, identify if you have any ionic compounds, and if you do, make sure that you have neutral products using our identifications of ionic and molecular and neutral